So my name is Roland Schmehl, and I will introduce you to Airborne Wind Energy together with Jelle. And Gerard, I hope that we can contribute to the paradigm shift. I think that's a very good way to see it. Here you see a kite flying and producing energy on the island of Aruba, next to the Father Pete wind farm that you see the turbines in the background. That was a very nice setting of Kite Power, our spin-off company, in 2021. This should also be animated. Okay. This is how the concept works. So we fly a kite connected to a tether to a ground station. The ground station has a drum with a connected generator. We reel off the cable, the tether from the, let me try this again. Oops, is there a way to back? Sorry, can you run this video again? Okay, so we fly these figure-of-8 maneuvers to pull very hard on the tether, and that's when we produce the energy in the generator. Think about a yo-yo. Once we reach the top, the maximum length of the tether, the kite is depowered and pulled back by the motor. That consumes a little bit of energy, but netto, we actually produce energy. So we do need storage, also very important for this type of concept. There are a few, let's say, opportunities or advantages why we go towards kites, and of course we also have our challenges. As for the opportunities, a kite needs a lot, or an airborne wind energy system needs a lot less material than a wind turbine. If we go offshore, we calculate something like 90% mass reduction for the same amount of energy. Then the kite can be adjusted to the altitude. So if the wind blows stronger at higher altitudes, we can fly higher. If it blows harder at lower altitudes, we can fly lower. So this adjustability increases the so-called capacity factor of our system. And of course, you can imagine we can transport the system much quicker to a location, deploy it there, then move it somewhere else. So we have increased mobility. On the other hand, a flying kite and operated from a ground station is more complex. There are an infinite amount of degrees of freedom by flying the kite. That all needs to be controlled. Also, the ground station needs to be controlled. We require reliable and robust control, and we depend on high performance materials. You see here the tether is made of Dyneema. That's a plastic material that is stronger than steel, and also the kite itself is made of plastic. And of course, the regulatory framework needs to be adjusted. Okay, 2 slides with a bit of technical content I have to introduce. The material use, that's one of the advantages that I discussed. You see here, this unit is the mass percentage of a 100 kilowatt system that has currently been manufactured. You see all this is the ground station. In relation to this, the kite control unit, the little robot that controls the kite during the flight. We will see this in later slides. The tether and the kite are small contributions compared to the ground station. In a wind turbine, this is actually a reasonably small part. The nacelle and the generator makes up for 20% together with the rotor in terms of mass. You see here that all the mass is now in the generator, and for the rest, very little material. We also need to think about the replacement of the materials here. Kite tether, mainly because they degrade over lifetime, so they have to be replaced. That's something we need to take into account, and we did that here in a study. Global warming potential is another metric, so the CO2 equivalent per megawatt hour energy produced is here distributed over the components, and you see again the ground station is the main factor. So What's clear from these pictures here is, from these diagrams, is we can dramatically reduce mass, a bit less dramatically reduce the environmental impact, but still significantly. That's one of the key drivers for our motivation to go into airborne wind. And then a second important driver is, you see here, power curves for a classical turbine and a kite power system, which can fly higher, as you see here. We can harvest at lower ground wind speeds than the turbine, meaning this region here of wind speeds we can actually exploit. And that has to do with this adjustability of the operational altitude. So, and from now on, I think I have mostly graphics. In Delft, we had a pioneering team, I think, one of the earliest, but by now, airborne wind energy is researched and developed all over the world. You see here maybe a few highlights. In the US, we have wind lift, and then in Europe, kite power here in Delft. We have Kite Mill in Norway, Sky Cells in Hamburg, and Enerkite in Berlin. But there are many more institutions involved. These are the current sites where airborne wind energy is tested, partially already commercially. You see most of the sites, the green ones are the active ones. They are in Europe. Here in Ireland is the test center of kite power, and also in the Netherlands we have some operational sites. But since 1 or 2 years, China is actually ramping up. And you see that they have some sites now with quite large facilities installed recently. It all started here in Delft with Wubbe Ockels. This is a photo from 2013. He was the pioneer of airborne wind, patented the Laddermolen in 1999. And from this moment on, basically, we have a continuous, let's say, build-up of knowledge and publications, also spun out 2 companies, Ampix Power and Kite Power, I think 2 important players. A few images of how this early research looked in Delft. You see here snow on the airfield at Falkenberg. This was our ground station, tether going up into the air and flying. Here the crew on the control center, over here in the background, one of the members trying to hotfix some bugs in the flight software. And then this is how we launched the kite in these days. This is a 25 square meter kite, our so-called V3, with 3 students here holding the kite so that it doesn't fly off. Another one holding the tether with the kite control unit here. In the foreground, you see this kite control unit uses 2 micro winches on tapes to actually control the kite like a kiteboarder does. And it's wirelessly connected to the ground station where the control center is. And then countdown, then we lift off, and then we are flying solo. You see here the kite, the ground station at Falkenberg. Controls needed to be in check at the time. We already had automatic control. So once the kite was launched, we could press a button and it would gently fly, figure of 8 maneuvers, harvesting energy. And in the evening you have to land. All was done manually, and you see this is maybe not the most safest thing to do, but nothing happened, luckily. And then we wrap up and go home. Winter conditions demonstrates, kite flies in snow, absolutely no problem. We then were lucky to get a larger EU grant. Actually, that was, I think, Hester Beil, our dean then. She was the one who signed the grant agreement, which is something really nice. And with this grant, we were able to develop a large ground station, a 100 kilowatt ground station, hire a team, and then collaborate with 3 European partner companies to commercialize the technology. And this is a picture from a few years ago, also here on an island near to Zeeland, where we used the kite to charge an electric car completely off-grid. I think this is one of the application scenarios you can think of. Our research group a year ago and Kite Power here in Delft in the Kabel district. They have a large facility there, and I think this is the 60 square meter or the 100 square meter kite. Would you know?
I think it's
the 100 square meter. Yeah, it's pretty large. So this wing gets larger and larger to pull more power from the sky. And that's a very nice feature of kites. They are easily scalable without too much costs. And the bigger the surface area, the more power you can get out of the wind. Then we were also lucky to be able to establish a test center in Ireland with the help of RWE. You see here the ground station with battery, then the hangar of the test center. And I think since about 2.5 to 3 years, the Irish crew is continuously testing new kites on a weekly basis, I think 2 or 3 flights per week. Also using operators from Ireland who were trained and certified kite pilots, which is a new profession in our field now. That's the Delft team visiting Ireland. The operations in Ireland, you see, it's peat. You cannot go there by car, so the kite needs to be transported to the launch site with this vehicle and then put on a launch trailer and unreefed. So all these operations are not manual anymore, but automated with mechanical infrastructure. That's the onboard wind turbine suspended below the kite for the avionics of the system. And maybe just before I finish with the video, a few key numbers. So we are now looking at 24-hour continuous operation of the system before we land, typically. That's the 3.1 million of deployed projects that we have executed since the foundation of the company, flown more than 400 times, 24 employees, and we have these 2 locations, one in Delft and one in Ireland. And if you could get this video to run with audio, please.
At Dura Vermeer's modern construction sites, electric machinery is already in use. Working without emissions is becoming essential. But can we do even better? As the wind rushes past us, we ask ourselves, can we harness its power? And what if we could turn that wind into energy? 200 meters up, where the wind is strongest, we're putting it to the test. As the first construction company in the Netherlands, we're exploring whether airborne wind energy, generated by Kite Power's kites, can provide reliable power for our work sites. A mobile system instantly ready to deliver. The kite loops in figure eights, pulling hard on a cable. The cable unspools from a drum, driving a generator that transforms motion into electricity. That power is stored and managed on site, silent, flexible, and independent of the grid. It opens up new possibilities, especially where traditional infrastructure can't reach. Power for tools, power for machines, like this Volvo truck, already electric, now driven purely by wind. Dura Vermeer aims to lead. That's why we innovate, with pioneers like Kite Power and Greener Power Solutions, who enabled seamless integration between kite and battery, turning wind, flight, and smart storage into zero-emission energy on site. We're searching for answers. Can airborne wind power become a stable part of our sustainable future? Can we reduce our dependence on fossil fuels and build in quieter, cleaner ways? Every test, every data point, every breakthrough brings us one step closer to the energy-neutral construction site of tomorrow. We're not doing this because it's easy. We're doing it because it's worth exploring. Dura Vermeer, realizing ambitions.
Thank you. I think with this, I would like to hand over to Jelle. So Dura Vermeer was our first commercial customer, and I think they were quite happy about what we did for them, and that's why I wanted to show this. Please.
Thank you. Oh, nice. Yeah, then we get to my topic. So for me, it also started similar to how it started for Wubo, the first Dutch astronaut who loved kites since he was a little kid. It's a bit similar for me, but I like to go on the water with them. And these days, the kites are not only used to produce energy and not only used to pull people across the water, but also boats. And the kites are getting bigger and bigger and bigger, similar to the wind turbines, which were also getting bigger and bigger and bigger, right? Slowly starting to produce more power. And it's interesting to look a bit into how these kites actually work. And for that, I have a nice video here. And it's a bit similar to, there we go. A bit similar to how a kitesurf kite works. One pulls on the lines, and this creates a deformation in the wing. So the wing initially is nice and straight. I pull on one side, the wing rotates, and as a consequence, the aerodynamic force factor also rotates and the whole kite starts to roll. And in that way, we can steer the kite left, right, everywhere we want it to go. And if you want to simulate this, you need something called fluid structure interaction simulations. And that's quite a mouthful, but I will talk you through it. So first, we take a shape here on the right, and we use an aerodynamic model to get an amount of force, an aerodynamic force. Then we give those forces to our structural model, which now computes the new shape based on the forces. But then we have a new shape, and we need to give this shape again to the aerodynamic model, which based on this new shape gets a new force, and so forth, and so forth. And these iterations we solve using computers, of course, and the computer is getting faster and faster and faster, and that allows us to include more and more details. And as I said, to do so, we need an aerodynamic model, and we need a structural model. We use all sorts of modeling techniques for this, but I will not bother you with that today. I think what's interesting to highlight is why actually are these simulations so relevant? Well, with the kites becoming bigger and bigger and bigger, we can no longer use traditional methods that we stole from the kite design, the kite surf industry, where we take the kite to the beach, we fly it, and we feel a little bit how it works, and then we're like, no, it's not right. This doesn't work anymore at 200 square meter. This is too big. We need to predict it upfront to optimize our controllers, to optimize our flight path, to optimize our design. Because what we do not want is that the kite, because of misprediction, falls out of the sky. Oh, video not working. Anyways, so the question arises then with these simulations, are we making the right predictions? Because if we're not, then what are we basing our optimizations on? And to answer this question, we need to go to the wind tunnel. And in the wind tunnel, we can start simple. We can take the kite, slice it in half, take the airfoil, so as it's called, and we place it inside the wind tunnel. Then inside there, we can rotate it around, put some flow to it, measure the forces, and we can see if we make the right simulations. We can also go one step further and look not only at the external loads, but look at how the flow behaves itself. And one way to do that is using oil. And then you get beautiful images. To me, this is supposed to be science, but it's more art, right? Here in the front, the illuminated part is the so-called laminar separation bubble. And then slowly towards the back, we see it fading and gravity taking over and dripping the oil flow down. Besides oil flow, we can also use other techniques, stethoscopes, infrared cameras, and then we can study things like the transition from laminar to turbulent, where first the flow is laminar and then it goes to turbulent. And the stethoscope shows the same story. because when the flow transitions from a laminar to a turbulent state, it becomes a lot more noisy. And the stethoscope essentially is a microphone, and this allows us to hear this increase in noise. So then, once we're done with the airfoil level, right, the midspan slice, we go to the kite level. And we take the kite and we put it to the wind tunnel, which exists thanks to legends like Gerard, thank you. And then we can do some really cool measurements using carbon fiber kites to check out again, what are the loads, how is it doing, how do the smoke trails go over the wing, is it as we expect that it would be. And then once we're done with the loads, we can go back and go one level deeper again. How is the flow actually behaving? What is the flow topology? How are the structures looking like? And for that, we need lasers. And I hope this video works. Nice. Yeah, so this is how it looks like when you're testing with lasers inside the wind tunnel. It's very chaotic. But if you look well, on the left, you can actually see the kite standing in the flow field. And I'll explain briefly how this actually works. So we use a camera, we use a laser, we use a smoke machine, and then the smoke particles, they're accelerated by the wind turbine that powers the wind tunnel. And these smoke particles we illuminate with the laser, and then we take pictures of those particles, and then we do a lot of algorithms and coding and processing and whatnot, and then we find something about how the flow actually looks like. And we find something about the flow structures, the magnitude of the flow around the airfoil. And then, of course, the question is, do these measurements relate to the simulations? And yes, we see the same flow structures back. We see the same areas of high velocity and low velocity, and curvature and wake and vorticity and whatnot. So this is all aerodynamics. But as I said, the deformations are critical. So we need to also look at how the kite shape moves. And for that, we can do in-flight measurements. This is a very recent picture, and I think that's also the reason why I am here today to talk about what is happening right now in wind energy. What is the state of the art? This was made last week in Ireland. The people are all in the crowd. Thanks for coming. And what was used here were cameras to track markers around the kite. And by tracking the markers, a bit the same as with our eyes, using two cameras to track the markers, you can track their relative position, and you can check what the shape changes are over time and overlay that next to the simulations. And by doing these kinds of efforts, we hope to build better and better models, and these models can then be used to build better and better kites to produce more and more electricity. Thank you.